Hello there, my name is Wyatt Mingus, and I'll be walking you through my team's design of a predictive maintenance system for Navy jet engines. Our system works to improve on the existing preventive system, which uses a calculated failure rate to determine when best to make repairs and to do them in advance of any failures that will occur. We seek to use a predictive method, which instead of simply doing repairs based on observed historical data, we would take the actual engine sensor data, feed it through a machine learning process to determine when best to schedule maintenance so that no unnecessary repairs or maintenance actions are done, thus lowering maintenance costs and improving fleet availability. To begin with, we'll go through our context analysis. Aircraft operations require maintenance to successfully perform mission needs such as transportation, surveillance, and combat. And aircraft maintenance is composed of pre- and post-flight checks, line maintenance, and heavy checks. And the frequency of line maintenance creates the opportunity to increase the operational efficiency by optimizing the scheduling of these particular checks. Now, currently, the Navy aircraft availability rate of their planes is under 70% using the modified Department of Defense value for availability, which only calculates this number using engines that are not put in storage. The Navy goal for availability is 80%, so these numbers are well below that. Now, there are three main types of maintenance actions. The first one is preventive. This is time-based and using a reserved failure rate from historical data. It's performed early to retain aircraft reliability before failures occur. Corrective is unplanned, performed after a point of failure, and leads to unscheduled downtime, negatively impacting aircraft availability. This can occur from manufacturer defect, improper use, wear out, or random error. Predictive is condition-based and utilizes an aircraft remaining useful life, which is calculated as the total number of cycles up to failure. This increases the time between maintenance actions, which reduces downtime. Now moving on to our concept of operations. The current as-is process is preventive maintenance. The current maintenance planning uses scheduled maintenance to proactively retain aircraft performance reliability. Engine repairs are done to components through the observed failure rate. It's important to make sure that not too much preventive maintenance is done, as that will result in unnecessarily high costs, and make sure that's not too little done too late, which will result in unnecessarily high corrective maintenance costs. Currently, the maintenance process works between the flight operations group, maintenance planning, and supply chain, and the bottleneck is in the area shown in red, which is MP.2, calculate CPUT across fleet, and MP.3, develop maintenance schedule. Here we'll move on to our stakeholder analysis. Our primary stakeholders are flight operations officer, supply chain management, engine manufacturers, and the maintenance crew. Of these, the largest tension comes from the engine manufacturers, which rely on repair services to leverage a profit margin. Most money for these companies is not made on the initial engine sale, but rather on the constant maintenance these engines require. And so these maintenance and replacement part fees are where they make the majority of their money, so reducing maintenance actions will cut into their bottom line. Now we'll move on to our problem and need statements. So the current preventive methods used by the Navy fail to meet their aircraft availability standards of 80%. The Navy inventory of fighter jets using turbofan jet engines currently have an availability of about 60% as of 2020. Our problem is that the current preventive maintenance methods used by the U.S. Navy result in an availability of turbofan aircraft 20% lower than their goal of 80%. The past 20 years shows a mean availability deficit of 13% with a standard deviation of 10%. There is a need for U.S. Navy turbofan aircraft to increase availability by reducing the amount of time aircraft spend in maintenance without sacrificing reliability. Should I now move on to our 2B process? Our 2B process is condition-based predictive maintenance. This allows us to replace current preventive maintenance methods. We will analyze aircraft engine sensor measurements and implement machine learning to predict engine remaining useful life. We will then schedule maintenance using simulation with integer programming to optimize schedule. Aircraft operations will benefit from increased efficiency in maintenance planning, and engine manufacturers can advertise superior engine performance to sell engines at a higher price. This change will allow us to move from our preventive process to a predictive process as shown here, eliminating the bottleneck as identified in this area and transitioning it to this system here. This will use data collected from the sensors instead of historical maintenance performance data, and a new system MP.1, which will process sensor data and generate maintenance schedule action, will be used instead. First, we will check to see if there's a new engine. If it is a new engine, we shall first model degradation, then generate simulated run to failure data. If it's not a new engine, we'll just use existing testing and training data. This will then go into MP1.3, which is the REO prediction of false classification, which then feeds into an action that generates optimized maintenance schedule. Now on to our requirements. For our system, there are 4 main mission requirements that are then decomposed into 43 total preventive maintenance requirements. The first one is that the system should generate simulated run to failure data for each single and double failure mode of the turbofan engine given its different components. Then the system shall simulate the RUL for each given aircraft with a type 2 error of less than 10%. Then we shall make sure the system shall schedule the next maintenance action for a given aircraft by date, time, and type of maintenance. Then the system shall also identify the next maintenance actions for a given fleet of aircraft with an availability of at least 80%. Moving on to our functional description. Here we have our 5 main components of our functional architecture. First, in F.1, we collect sensor measurements. Then, we move into a component degradation model, with the output from that being engine health parameters and engine wear thresholds, which go into generating the engine run-to-failure data. This will then feed into predicting and classifying the faults, which would then be allowed to be sent to the generation of the optimized maintenance schedule done in F.5. The collecting sensor measurements will be done very early on by the actual operators of the planes themselves. Then the component degradation model and the generated engine run-to-failure data will be performed by us prior to providing clients with the model for them to use to optimize their maintenance actions. Then, once we're actually on site and the software has been provided, we will then predict the RUL and classify faults with the data we've received from them after the completion of these other ones. Lastly, this should be fed directly into our GUI and our program, which will allow us to then generate an optimized maintenance schedule. So this will be what the user actually interacts with, which is F.5. Moving on to here, we will go into our verification testing. So for the first mission requirement, we need to make sure it falls within the boundaries of pre-existing data generated for CMAPs, which is our digital twin we're using. So we'll run the MATLAB script for this particular digital twin, and then we'll make sure that our data falls in line with the thresholds and with the values generated from the pre-existing data identified in existing literature. Our success criteria is that generate engines fail in distinct ranges throughout the existing data without producing outliers. And results show that the generated run-to-failure data expands upon the existing data sets by generating data across identified operating flight classes for each type of engine component failure mode. For our second mission requirement, we will use CMAPs, or digital twin, to generate run-to-failure data for each single and double turbofan engine failure mode. We will then run the Python script to truncate designated run-to-failure data and document the true RUL for testing. We will then run the LSTM, or neural network, Python script to process the run-to-failure data and predict the RUL for each input test engine. We will then run our script again to classify the fault of the generated data by failure type. The success criteria is that RUL prediction for type 2 error would be of less than 10% with engines that fail within 50 operational flights. And classification accuracy needs to be at least 90% for single and double failure mode of run-to-failure data. The results show that a decreasing the learning rate and increasing the epochs of the LSTM increase the overall processing time results in a 100% pass rate for RUL predictions less than 50 hours. For 3 and 4, we worked on these verifications simultaneously, but the setup being to create input parameters of different maintenance actions. And the procedure would be to enter the input parameters into the model with random RUL values for each component. We would then run the model in random failure simulator. Our success criteria, the schedule class will match the output of the CSV files from the system, so that you can then export the data and look at the maintenance actions more directly, and the model produces scheduled maintenance actions and deploys aircraft emissions of given fleet sizes, and given maintenance stations and technicians. The optimization program scheduled maintenance actions resulting in less than 10% type 2 error, and the fleet availability is greater than or equal to 80%. Moving on to our validation testing. These are the overview of the validation test plans we have for mission requirements 1 through 4. The first one requires us to plot real and generate sensor data using control charts, and then test for acceptable covariance of paired and collected measurements. Then, for the second one, we shall follow a predictive maintenance schedule with a small group of at least 5 aircraft, and then use until 100 cumulative maintenance actions performed across the fleet, and validate no more than 10 aircraft underwent corrective maintenance. For the third one, we will test a small group of aircraft using current preventive methods for 5 weeks, and then calculate the total maintenance costs and aircraft availability for both predictive and preventive, and validate that the total maintenance cost decrease and fleet level availability increase by at least 10% each under the predictive. And for the last one, we will test a small group of aircraft using design predictive methods, over 5 72-hour periods, and validate the fleet level availability for at least 80% over each period. Doing a case study with Monte Carlo experiment we did, we found that the mean preventive availability was 75%, the mean predictive availability was 92%, with a 17% decrease in availability with predictive methods and a 45% decrease in total maintenance costs. We also saw that the mean time to repair each component increases, the predictive performance is sustained, while the preventive performance degrades quickly. Lastly, moving on to our business plan. Our product is a trained predictive model and decision support tool for jet engine maintenance, and used to replace traditional jet maintenance scheduling, and will be marketed to the 64 military wings. Our 5-year ROI is 353%, with an investment cost of $176,000 and $250,000 average salary per employee, and a $350,000 annual marketing cost. Our revenue will have an annual unit price of $500,000, and we'll have hopefully a 10% annual market penetration, with a goal to break even within 1.6 years of penetrating the market. I would like to take a moment to thank Dr. Casey Chang, who is a professor at George Mason and also our advisor for this particular project. We'd also like to thank Zhenyang Fan, who's a graduate research assistant who developed the neural network used in this project, as well as the optimization equations. Thank you so much. If you have any further questions, feel free to reach out to us at any time. Thank you.